Ready to save 50% on hundreds of marketplace products? Well, we've got some good news. Now through Friday, April 17th at 11:59 p.m. Eastern, more than 750 select products are on sale during the April flash sale. With organizational tools, photoreal and stylized models, material collections, effects, and more, there's something for everyone. Are you a university student looking to learn Unreal Engine? Unreal Fast Track is a new 5-week online challenge for students around the world to learn Unreal, gain industry-relevant soft skills, and attend Q&As with game development professionals. Get all the details and register today at unrealengine.com/fasttrack. With the successful advent of the Nintendo Switch, developers now have an exciting new unique platform on which to release their products. For many studios, this opens up the possibility to expose previously released games to an entirely new audience. Read Bulkhead Interactive's journey on bringing their 2016 puzzle game, The Turing Test, to Nintendo Switch, where they discuss their process and design decisions to make the most of Nintendo's versatile handheld platform. Unreal Engine 4.25 Preview 7 has landed on the Epic Games Launcher and GitHub. Now's your chance to test drive the latest features. Download Preview 7 and share your feedback on the Unreal Engine 4.25 Preview forum thread. Raccoons, Cars, and Marionettes. The creators behind Backbone, Dead Static Drive, and A Juggler's Tale shed light on their unique inspirations and what fuels their creativity in the latest additions to the refreshed Revving the Engine series from Unwinnable. Dive into their stories of horror, anthropomorphic animals, and puppets, then keep an eye out for more adventures into the minds of the creative Unreal community. Now for the top weekly karma earners on Answer Hub: Everynone, Clockwork Ocean, F. Sapio, Vice Versa, Vacherka, WeFit Trainer, A North Star, Black Force Dragon, Xenoblast, and Shadow River. Thank you so much for helping out others in the community. Over to our first community spotlight, The Last Goodbye by Labidi Wassef. The scene was a practice in building realistic procedural landscape materials based on the idea of a hero who had to leave his homeland for battle. What a beautiful piece, and check out more of Wassef's work on their ArtStation page. For those of you who would like to use a 3D mouse or space navigator, try out David Mraz's Space Mouse plugin, which allows you to control any 3D editor viewport in focus with 3D Connection Space Mice. Find out more about the plugin on GitHub and try it out for yourself. Our final spotlight is Alchemy Story, a casual farming sim in which you play as an apprentice alchemist, where you'll discover a world of magic, cute creatures, and adventure. Grow your garden, brew potions, care for your pets, and meet new friends. Alchemy Story is now available on Steam. Thanks for watching this week's news and community spotlight.
Hi, and welcome to Inside Unreal, your weekly show where we learn, explore, and celebrate everything Unreal. I'm your host, Victor Broden, and I'm here today with Mike Lyndon and Paul Ambrosiussen, two technical artists at SideFX. Welcome to the show.
Thank you.
Hey.
Hope you're doing all right. Would you mind talking a little bit about what we're going to cover as a topic today?
Sure. Paul, you want to go?
Yeah, of course. So I'll kick off the stream with a couple of world building focused topics, such as the building generator. I'll be talking about how you can take OpenStreetMap data, which is sort of like a Google Maps type website online, but in like a public format. So you can just download it, bring it into Houdini, and then use Houdini Engine to generate buildings, roads, and lots more straight inside of Unreal. After that, we'll be talking about a new tool that we've written to export point clouds, which you can use with a new plugin that Epic recently acquired and published for free for use with Unreal. And then we'll be looking at an algorithm called wave function collapse and how we've implemented that in Houdini so that you can use it to use it for world building, in this case, a dungeon generator. And then I'll give it off to Mike.
Yeah, and I will be looking at the Houdini Niagara data interface. So we showed this, I think, about 2 years ago now. But since then, Niagara has kind of come forward in leaps and bounds, and so has the data interface. And so it's a way of getting point clouds from Houdini into Niagara. And today I'll be showing you how to use that for fluid sims, for crowds, for general setups where maybe the simulation process can't be run at real time, and so you can blend the power of Houdini with Niagara to create some pretty cool stuff.
Sounds exciting. Paul, would you like me to kick off the slide?
Yeah, of course.
All right, we are good to go.
Awesome. So just a quick disclaimer for people so they know why I will be saying next slide a lot. Victor is actually running the PowerPoint. I'm just looking at a screen share of the PowerPoint I sent him. So please ignore me saying next slide a bunch of times. So first off, shout out to Crab Champions, which is the image you see here on the front, which is a really cool game that's in development. Check out their Twitter to see more information on that. So let's get started. Next slide. All right, so the topics we'll be covering today in the first segment of the live stream, like I said, is wave function collapse, which we see in the top left, which is used for a dungeon generator inside of Unreal. We'll be talking about the building generator, which can generate a city, streets, trees, and lots more cool stuff, which you see in the bottom right. We'll be talking about the point cloud exporter, which can bring, let's say, a LiDAR scan or photogrammetry scan or anything else you generate in Houdini straight into Unreal. Let's go to the next slide. All right, so before I start talking about those tools, I need to talk a bit about where you can find those tools and what they're part of. So these tools are part of SideFXLabs, and SideFXLabs, as you can see, is a completely free open source toolset geared towards assisting Houdini users with a variety of tasks commonly used with digital content creation. Our primary focus with this toolset is still game development, because the tool used to be called the Game Development Toolset with Houdini, but we gave it a rebrand to sort of allow us to expand a bit on the sort of industries that are using this toolset, because we've seen lots of use recently in film, TV, ArcViz, AR, VR, and lots of other industries. Once again, it's open source. It's free, so you can download it, check it out, see how the tools work, even extend them or build something else completely from it or learn from it. It has over 150 tools, which is a lot on top of what Houdini already has to offer. And the tools mainly focus on workflow and UX. So it tries to make your life as a game developer a lot easier, right? So if you were to, for example, have to create networks of nodes inside of Houdini yourself for a very repetitive task, there's probably a tool that does that for you in SideFXLabs. Let's go to the next slide. All right, if you want to learn more about SideFXLabs, besides what I just told you, you can go to our website, and then under the products tab, you can find a new entry called SideFXLabs, where you see this sort of overview, which also links to a bunch of videos talking about the tools. And there's also another tab which shows the actual tools that are part of the toolset. So here you can find those 150 plus tools and a quick description of what it is they do. So if you want to find a tool for a specific purpose, you can probably just go to this website to find, type in building generator, and it will show you, okay, here's a tool that generates a building for you. And of course, it also has a link to a video that shows you how to install SideFXLabs. Next slide. All right. So before I begin, lots of the stuff that I'll be showing today uses Houdini Engine. And most of you, if you're a Houdini user and you've been using Unreal, you've probably used Houdini Engine. I want to give everyone a quick update on Houdini Engine version 2, because that's something that people have been waiting and asking for. I'd like to let you know that in this stream, we're not covering that plugin. The stuff I'll be showing is using the version 1 of the plugin. But the short summary is that we're expecting to go into alpha very soon. But the development is progressing really nicely. We're testing lots of stuff. But if you want to know more updates, please go to a forum post that we have on our website. I think Mike will be posting a link to that forum post specifying or talking about the development in the chat for you. So that's just some information for those that were looking for it. So what is Houdini Engine? Houdini Engine is basically an API which allows us to create plugins, in this case, a plugin for Maya, Max, Unity, and of course Unreal, that allows you to take all the sort of procedural assets you've built inside of Houdini, let's say a fence generator or a building generator, right, which we'll be talking about today, which allows you to play with sliders, to modify the properties of that building without having to modify any vertices manually yourself, which is the power of Houdini, right? Proceduralism. If you were to export that to, say, Unreal with FBX, that would be a static mesh that you can no longer modify inside of Unreal. Well, with Houdini Engine, you can take that proceduralism that Houdini has and bring that power into Unreal, so that now you have access to those sliders, to modify the number of windows or anything else like that, straight inside of Unreal. So that reduces the number of round trips you have to make between your engine and the DCC you use to create content. Next slide. So first we'll be talking about the building generator. So here we see a quick image of what the building generator could produce for you. So if we go to the next slide, we'll be seeing this tutorial page. So everything I'll be showing today about the building generator, all the files that I'm showing and running through, which is just an overview in this stream, you can find more about on this tutorial page. So if you go to our SideFX website and look for city building with OSM data, you'll find this tutorial series, or course rather, which has, I think, 4 videos talking about all the different steps that I'll go through today. And it also gives you all of the project files that I'll be showing today. So if you want to replicate exactly what I'm showing today, you can just go to that website and download the files. Next slide. All right, so how does that look like inside of Unreal, and what do you get? So as we can see, everything you see here is generated with Houdini and Houdini Engine. I haven't placed a single asset manually in this scene that I'm currently flying through, right? And on top of that, none of the object placements, the street placement, none of that I've done myself as well. This is actually the city layout of, I think, Toronto, of small part of Toronto. Next slide. So how does that look like and how quick is it? Well, first of all, let's download the data we need from OpenStreetMap. So go to openstreetmap.org, zoom in to a location you like, New York, LA. In this case, I'm going to Toronto because that's where the SideFX headquarters is. And I just pick a random place in Toronto. I don't have a specific reasoning for this location. It's just where I landed, when zooming in. And then click export, and that allows me to marquee select a region that I'd like to export all the street data from. So the streets, the rivers, the buildings, street names, and everything else that's on there where OSM has data for you from. So then, of course, we want to bring it inside of Unreal, because we don't just want to look at a map. We want to have a 3D city we can run through. So we create our HDA, our Houdini digital asset, which is using Houdini Engine to cook everything. And we tell it to use that OSM file to generate our city. And then, of course, needs to do some cooking, right? It needs to calculate how do I process these curves into streets, and how do I convert these building profiles into actual buildings. And then voila, we already have that exact location that I just downloaded from the internet as a 3D playable scene inside of Unreal. So that, of course, was very easy. It's, of course, a pre-made HDA that you can download, like I mentioned before. So let's take a somewhat more deeper dive into those HDAs in the next slide. All right, so what is it that Houdini generates and brings inside of Unreal? It didn't generate one giant mesh, right? Because that wouldn't be optimized. You'd want instances using assets you already have inside of Unreal. That's what Houdini Engine allows you to do. Generate a point cloud and then assign something called an attribute value, which is just a property of a point, of all the points you see there. And then it tells Houdini Engine, this point at this location needs to instantiate this piece of geometry, which can be a window, it can be a wall, it can be a piece of a street, it can be a light post, it can be a garbage can, it can be anything you want, right? And then, of course, as you can see, there's also some polygons, and those are just pieces of unique geometry that Houdini is generating and is also exporting into Unreal. So go to the next slide. All right, so let's see how we can build that from the ground up, because that still doesn't tell us a whole lot. First of all, we need to import the data we downloaded from OpenStreetMap into Houdini. So we just go to our download folder and we bring in that file we just downloaded from the internet. And that gives you this using the OSM input node, which once again is a tool from Labs. And that has lots of attributes talking about properties of those curves, the width of the road, number of lanes, how tall is this building, and so forth. Then with the OSM filter, we can filter out data we don't like. So in this case, I just want the building profiles. So I just drop down an OSM filter and tell it to only keep the building profiles. Next up, we plug it into the OSM buildings node, and that already gives us 3D blockouts of every single building. Next up, we're going to need the street. So for that, we drop down a filter again. We turn off buildings, and in this case, we want the roads. I can then specify what type of roads I want to keep. In this case, I just want the primary road and the secondary roads, which is, let's say, a highway and then a main street. And then, of course, we need to generate streets from that. So that's what I'll be using the road generator for. Plug that in, and voila, it already resolves all the intersections for us. And as you can see, that gives us this, this vertex-colored intersection. And what the vertex colors mean is those allow us to blend between multiple UV sets that it uses to blend between textures, so that we can use a tileable texture on this intersection without having to create unique textures per intersection, because that wouldn't really be optimized. Then we can modify any of the properties on the parameter interface for the road, right? We want to modify how wide is the intersection, how curved is it, because that's not something that the OSM data holds, right? And already you can see that we have, something that looks like a city inside of Houdini with maybe, 5 minutes of work or less. Next up, we need to process. Oh, we're not done yet with that video, I think.
Is there a way for me to forward back to that?
I think you just, yeah, if you just put your mouse on the slide, then you have a time bar. So if you just play and then go towards 3/4 or something.
Are we about there now?
Yeah, perfect.
Cool, sorry
All
about
right.
that.
No worries. So then we, of course, need to process every one of those blocks. I think you need to hit play again on that on the left side. Yeah. Oh, that's a Houdini play. That one. Yeah.
That was not
So
confusing
then, of course, so then, of course, we need to process every one of those blockouts to become a building, because we don't just want that, blockout. And for that, we can use the building generator. Plug that blockout in, and that converts it into a building. In this case, it just uses some default properties to already cut it up in like a default preset that I've created. But that's something that we will look at on the next slide. So what does the building generator allow us to do? It allows an artist to create building modules for, say, a window module, a door module, a wall module, a corner module, a ledge module, and of course, lots more. And then it allows you to specify in the parameter interface, which is the part you see in the middle, the gray strip. It allows us to tell the tool that we want to use a particular module for the generation of the building. So we can, for example, say, use wall A for all the, the wall pieces and just repeat it, or use wall A and then wall B, and then repeat that sequence of wall A, wall B, wall A, wall B for the entire floor. It also lets us modify how tall we want the floors to be. It allows us to specify whether or not we want ledges, right? Because a floor might have a top ledge and a bottom ledge. And it also allows us to override specific properties for a specific floor. So let's say you want to have the first floor be twice as tall and use different modules, then that's something that we can also specify here. So as you can see on the left, it just basically cuts up that blockout we feed into the tool into building modules the artist created. So these can be procedural modules, like a procedural window or a procedural wall, but these can also be art direct or highly art directed art pieces that an artist crafted, to achieve a specific look. Next slide. All right, so how do we control that? I'll be running through this one building as an example, and then afterwards I'll show you how to do that for the entire city. So first thing, because it's easier if you're just working with one building, that it just is oriented on the origin, I can drop down a node called axis align, which will just take whatever geometry I have and center its pivot on the origin. Next up, because I like it to be aligned more, I can drop down a straighten node, and that allows me to select a face that is pointing up. and it allows me to select a face that is pointing sideways. And then Houdini will, based on those two normals of those primitives, realign that module so that it is perfectly aligned with the world grid of Houdini. So now let's take a look at what we can do to modify this default look, which doesn't look as great, and replace it with building modules. So the modules I'll be using here, are just some quick prototype modules. They're not, the highest quality art like you saw inside of Unreal, but it allows me to demonstrate the purpose. So first thing, we import, let's say, an FBX from disk, and then we use a building generator utility to specify that we're dealing with a piece that I'd like to call wall_A. This is just a name that I picked. You can call it my beautiful, wall, my beautiful window, just whatever you want. I then want to import a different module, which I'll be calling wall_B, so that I have, multiple pieces of geometry to work with rather than just one piece, because, otherwise it would look quite boring and repetitive. So then we plug it into the building generator so that it knows about the existence of those tools, of those pieces of geometry. And then we just let it cook so that we can see what we're dealing with. All right, there we go. And then, nothing has changed yet because we haven't told the building generator to use those modules. It knows they exist, but it doesn't know what to do with them yet. So that's when we start tweaking with the parameter interface. So first of all, I don't really need ledges for this demonstration, so I just turned them off. And then I tell the building generator, for every single floor, by default, I just want you to use wall_A, which in this case just happens to be a window, right? All right, and then now, like I said, I want to use an override. So I want the first floor to use a different module because, I don't want the first floor to look the same. I want that to be taller as well. So I can go to my floor height parameter and set that to a value of 3.5 in this case. And as you can see, it modifies the first floor and adjusts everything above that so that it can make sure that that override that the artist specified can fit. Next up, our walls or our windows or walls, in this case they're called walls, are quite repetitive, right? We'd like to add some variation, perhaps some spacing between the windows. So we'd like a small piece of wall between those. So then what we do, I just needed a piece of wall, so I'm just going to create a grid operator, which is just generates a grid or a quad in this case, once I reduce the resolution of that. And I then make sure that I offset the pivot or the geometry so that the pivot of the module is placed at the origin, in this case, the bottom right of our module. So I write a little expression so that it automatically offsets the geometry so that it fits, even though I modify any of the procedural properties above, right? So then I don't have to worry about scaling it later on. I then name that one wall C and plug it into the building generator as well so that it knows about it. Then we're going to use that facade module pattern to just add a little dash between wall A and wall C. And already it modified the generated building so that we now have a little wall between it. But I don't quite like the spacing, so I just reduce it by size in half, and voila, we already have something that looks a lot better. Of course, it's still quite repetitive. You can modify, add different variations of modules, or create a different pattern, like, for example, wall A and then a different type wall and then a window C, to make it look like a less repetitive building. But you saw the result of that in Unreal and how to make it look better. This is just a quick demonstration of how to use the tool. So on the next slide, so now we've generated our basic building, right, which is still quite repetitive and it's procedural. Artists will still want to have manual control. They want to fine-tune things, for example, specifically place a module in a specific location, and that's what the hand-placed overrides are for. So an artist can just take a module, in this case it was a door, and place it anywhere they want on the building, and the building generator will take that into account while generating the building and make sure that that placement that the artist placed down takes priority over whatever the building generator will generate. Another interesting fact about the building generator is that it's not gridlocked. Your building modules don't all have to have the same dimension. You can put them anywhere you want on the building generator and on the floor, and it will adjust everything around it to make sure that the thing you place down fits. In this case, it couldn't fit any more windows there, so it just generated a piece of wall that you can later on swap out to use any custom geometry you have, or just keep the wall and have that be just a wall. So that's that. That already gives us some more art directable controls over our building. But that will become quite tedious if, for example, we want to place fire escape ladders on our building, right? Which is just a vertical strip of modules we want to place on our building. So that's what we have volumetric overrides for, which you see on the next slide. So volumetric overrides allow you to basically just place a volume. In this case, I just took a box and told the box that you are a fire escape. And that will make sure that the building generator looks at that, that volume and knows, aha, the person wants to place fire escape ladders on the location that's within that box, instead of you having to type, you know, in the building generator, I want wall, fire escape ladder, wall, because that would, you know, not be a lot of fun. And of course, like you can see, that gives you lots of art directable controls together with the hand place overrides in a procedural fashion. Because typically, if you want to take a procedural system and give the user, you know, controls over overrides, that's typically where your tool would become destructive, meaning any changes you make, you can no longer undo in the, you know, with the proceduralism you did before. So that's what this does allow you to do. So it's more volumetric rather than replacing things manually, or hard coding it rather. All right, next slide. So that was a pretty boring example, right? But it can look quite cool if you have more building modules. So in this case, here's an example that you can also find on our website, this file, where we have multiple modules, and we have this blockout, which is once again just a box. And then I plug it into the building generator, and voila, it will assemble all of those building modules into something that actually looks quite cool. And as you can see, with the vertex colors in the window, that is one of the features that the tool allows you to do, which is pick variations of a module that you fed into it. So if you have different variations for a window, you can tell the tool, here's, you know, I want to have a wall, but you can pick any of the variations of that wall that I fed into the tool. So it gives you quite a lot of control over what you can achieve with the tool. Let's go to the next slide. All right, so we have one building. We have a rough idea of how that works. So how do we do that for an entire city? Well, that's what we can use something called a for each loop. And a for each loop in Houdini is essentially just a network that allows you to specify a procedure you want to do on every single input that shares a property. In this case, it's 3D connectivity, right? Because none of these buildings are all connected. And do that for every single object. So in this case, since I have, I don't know, let's say 30 or 40 buildings, it is going to do that operation, or 106 actually. It's going to do 106. It's going to generate a building 106 times, once for every single piece of geometry that I feed in. And already you can see, without all too much trouble, I now generated an entire city with that building generator. Of course, all these buildings look the exact same now because I didn't, you know, tweak any of the settings with the building generator. But imagine that you give every single blockout that you had in that city a property. For example, this is a glass building. This is a metal building. This is a brick and mortar building, and have different style variations for those buildings. Then already, you can create a pretty cool looking city. You might even be able to use any of the data that the OpenStreetMap data contains, right? That might have some properties that you could use to automatically figure out what type of building it is. So that's that. On the next slide. So how do we then replace these modules that we have inside of Houdini with pieces of geometry that we have inside of Unreal? Because of course, we don't want to generate one big piece of geometry. We want instances so that we can efficiently render them and call them and whatnot. So inside of Unreal, what you can do is right-click any object inside of the content browser, be it a blueprint, piece of geometry, a particle emitter, anything else like that. Just right-click it and click Copy Reference. And then on the next slide, we can see that we can use a tool called Attribute Value Replace, which allows us to replace the values we fed into the building generator with a path to that object inside of Unreal. So all the modules I called wall_A, I can just tell Houdini, don't use wall_A because Unreal doesn't know what that is, but instead tell it, use this piece of geometry you find in the content browser, which means that we can instantiate anything we want inside of Unreal. Next slide. All right, so there we go. And this is what that result would look like inside of Unreal. So, we have our buildings, our trees, and a lot more. So let's take a look at the trees. How hard is it to generate trees in Houdini? Next slide. We actually have a tool for that, which is called Quick Tree, which is not necessarily a photorealistic tree like something like SpeedTree generates, for example, but it is an example showing you how you could generate a tree. So you can take that and expand on it and improve it, which some people already have done. But it basically takes in a curve and generates a tree from that curve. So if I were to draw a curve, then in real time, Houdini would generate a tree from that, like you saw. We can then modify any of the properties of that tree, because once again, it is a procedural asset, right? That's what we want. We can modify, the number of branches, the curvature of those branches, how many we have, the bend that those curves have, whether or not we want leaves or how many leaves we want, so that we can, modify it so an artist gets the look that they want. But that's one tree. How can we generate a forest? Because that's the next step, right? Going from one tree to multiple trees. Well, instead of taking your tree and duplicating it and modifying any of the branches, we can actually, on the next slide, we can actually automatically do all of those processes, like we saw with the building generator with the for each loop, for every single curve. So the first thing we need to do is generate some origins where we want to scatter or place our trees onto. So I'm just using a node in Houdini called scatter, which allows me to randomly scatter points on a surface. In this case, I just use a grid, but you can, scatter it on the sidewalks like you saw, or you can scatter it on in a forest or on rocks or whatever you want. And then I'm going to use a node called attribute randomize, which is going to add some variations to each one of those points, right? It's one of those properties or attributes, like we call them in Houdini. And that will just automatically scale all of our lines to have that value that we gave it to create variations or more randomization, right? Next up, we don't want exactly straight trees. So I'm going to use a node called point jitter to sort of jitter the position of those points a little bit to make it look somewhat more organic. Perhaps not that much jitter, but it's procedural network, so we can go back and change any of those properties later on. Then we're going to loop over every single curve we have there and just plug in that tree generator so that we have a tree being generated for every single curve. And voila, without all too much work, we now have a forest of trees. If we want to have a different surface to scatter trees on, in this case, I just want to have a larger forest, I can go back to my original input shape and just increase its size, and everything downstream will automatically update to account for that. If I want to have more trees, I can increase the number of scatters. So in this case, I increase it from 21 to 25, and already we now have 25 trees. If I want to change how crooked the trees are, then once again, modify any of the properties of that point jitter, and already we can see that we have a different looking result. All right, next slide. So that was that for the building generator and the tree generator, which were the two most obvious things in the scene. Of course, we had the street generator as well, but that was just exporting point clouds, which once again you could replace the asset references for. Next up, the point cloud exporter. Oh, let's go back one slide. So that's a ROP inside of Houdini, which is a render output driver. And that allows us to take any point cloud in Houdini and export it in the XYZ format so that Unreal can read it using their new plugin. So in this case, I just had a 3D scan of myself, scattered points on there with the scatter SOP, and gave it some color so that it was pretty. And I clicked render so that it wrote it to disk. And then on the left side, we can see if we input that into Unreal, we have that exact same point cloud in our engine, which is very useful, for example, terrain generation or visualizing a LiDAR scan or for geometry scan or anything else like that, or just for pretty art purposes. Next up. There you go. So here we see that plugin that Epic recently acquired and now distributes for free with Unreal. Next slide. So if you want to use that plugin inside of Unreal, just look for this plugin on the Epic Marketplace, which is called LiDAR Point Cloud. It's free. You can just add it to your plugin for free, and that then allows you to bring in those point clouds from Houdini. Next slide. All right. So that was the point cloud exporter. Pretty simple, but pretty useful, so I wanted to show it. Next up is the wave function collapse tool. So this is a dungeon that we generated using that wave function collapse node, and of course some other Houdini magic, to create something that looks pretty cool, if I may say so myself. So this was created by an artist called Simon Verstraete, who used the SideFXLabs tools to create this content. Next slide. So as you can see, it's a giant level. All right. So if you want to find the specifics on how it works and replicate it yourself, or even get the exact project files, you can open up that project in Unreal. Go to our website, sidefx.com, and look for WFC Dungeon Generator, which has that tutorial series on there and also has the project files. All right, so let's take a look at wave function collapse on the next slide. All right, so what is wave function collapse? Wave function collapse is an algorithm that is basically a constraint solver. And cutting things short, it basically allows you to create content or more content from a small example that you provided using constraints. So imagine you have one of the small little bitmap images you see on the left, right? Those 16 by 16 images where you have a few buildings or a few plants. And then on the right side of that, we can see that we have larger versions of that and multiple variations of that automatically got generated from it. So it's a really useful algorithm that allows us to create more content by just showing the computer, or Houdini in this case, an example of what it is you want. So that allows an artist to be super lazy and just generate a level once on an image and then tell it, okay, now generate me 1,000 levels of that using Houdini, and you'll get 1,000 levels off of that. So how it works, I won't describe it all too much because I have a separate presentation on that on our SideFX website you can find. But it's basically a Sudoku solver. So imagine you have your 9x9 Sudoku grid, and you already have a couple of numbers placed in that Sudoku grid. All of the other cells can only have a very specific value so that it doesn't collide with any of the other rows in your Sudoku network, right? So that's what this tool does in short, but then with pixels. And next slide. All right, so inside of Houdini, of course, we don't want to deal with any Python code as an artist. So we've taken that logic and converted it into a tool for us. So we have 3 tools. I'll be showing 2, one of which is the initialize grid node, and that allows you to take an image, feed it into it, and it will already import that bitmap image for you as pixels that the wave function collapse algorithm can use. Next slide. Oh, I think we missed a part on that video. Can we go back? I think it wasn't playing.
Didn't autoplay. Here we go.
Okay, there we go. So this allows us to basically pick any of those example images. In this case, it's just a maze. And then we plug that into our wave function collapse solver, which will take that example and generate more from it. So to visualize that, I'm just going to place some grids and expand on the pixels so we can more easily see them. So as you can see, we already generated an output that is similar to the input image, but not the same. But it looks similar, right? So as you can see, by just modifying any of the properties of the solver, for example, how big we want an output to be, we can already generate more interesting content by just showing the algorithm an example. Here's my small 16 by 16 example. Generate me something that's a lot bigger at this resolution. And then voila, as you can see, it generates something cool. And already with this specific example, we can see that we could perhaps use this for level generation. And that's what we did for what you'll be seeing on the next slide. All right, so here I have an image, which I think is 32 by 32. That is just black and white, and the black in this case just resembles a room or a corridor or anything else like that. It's just walkable space, and the white pixels represent areas that the player cannot access. For example, walls or lava, because that's where the player would die. And then we can already generate a level from that, or something that looks like a level, right? So if we plug in what we see on the right side, we could get something that looks, what we see on the left side, which we can process further in Houdini to generate actual level data from. Next slide. All right. So there's something interesting that we did for generating the levels, which is doing a multiple of these wave function collapse solves. Because if we were to just generate a black and white image, we would just have the skeleton of our levels. So we would have the floors and the walls, but there's no interesting content in there yet. So then what we did is we generated another wave function collapse solve inside of the wave function collapse solve, like Inception, right? Because that's fun. So we wanted to do that, where we have this other bitmap image where, for example, the white pixels represent obstacles. They can be crates. They can be, I don't know, something else that you can run into and not go through. We have red pixels that might represent enemies. We have yellow pixels that might represent pillars or something else like that. And then it will automatically do a wave function collapse solve with that, which produces what we see at the bottom. And if we look at those two images, we can see that on the left side, on the bottom left image, every red pixel is positioned next to a white pixel. And this basically tells the algorithm all of the red pixels have to be next to the white pixels, which in this case, in our human mind, tells us enemies have to be next to an obstacle. If we then look at the output that it produced at the bottom middle, we can see that all the red dots are indeed placed next to the obstacles. So without writing any complicated logic, we can already tell Houdini or the algorithm, I want enemies next to obstacles. And the same goes for pillars. So it basically extracts relationships between objects from that image and generates content from that. Next slide. All right, so once we have those pixels, we of course, can't use pixels because that's 2D. We want 3D stuff from that. So what we can do is take those pixels and process them further inside of Houdini. So on the room surface, for example, we can scatter boxes, or on the yellow pixels we saw before, we want to instantiate pillars. So to visualize what we're working with inside of Houdini, I just extracted points from those pixels and placed objects there. So every white box you see represents a crate or a barrel. Every purple tube is a pillar. The chains you see there are just generated chains in Houdini, and the little, beige or brown blocks are little pillars that have to hold those chains together. And then the yellow is just lava, so that the player dies if they walk into it. Going to the next slide, but of course that's not what we'd want inside of Unreal. So instead of exporting those boxes and pillars, we want to instantiate the pretty art that an artist created, because that's what their job is. Our job is just to create cool levels from this. So that's where our point cloud comes back in again. So if we go to the next slide, we want to go inside of Unreal. We find our barrel that we want to instantiate and just do copy reference, and then go back inside of Houdini to replace the thing that we called obstacle in there with a reference to the bucket or the barrel or the crate or the pillar or the fire or an enemy or whatever, right? Next slide. And that allows us to place everything you see in this level automatically without any input or any manual input, right? So we can generate the level skeleton, the walls, the floors, anything else like that. We can instantiate functional enemies by just instantiating a prefab, right? Just a prefab of an enemy. We can instantiate dangerous lava, which is just a polygon with a material assigned. And even that material was generated inside of Houdini, right? Because Houdini can also generate textures, either by using something called COPS, which is our compositing network in Houdini, or using any of the plugins like our Substance plugin, for example, because your procedural assets can be combined with other procedural systems like Substance in Houdini. And then because it's Houdini Engine, all of the stuff that got calculated in Houdini, which is the geometry and the let's say procedural network shader from Substance, just get exported to Unreal and assigned automatically. We can also generate unique geometry, which is what the chains are. Those are not little chain links I instantiated. They're just unique geometry that I generated. We can instantiate obstacles. We can instantiate effects like particle emitters or even the Niagara emitters that Mike will be talking about. We can instantiate audio components. We can generate and assign textures, materials. We can generate and modify terrains and any blueprint. That I generated all of this procedurally doesn't mean that you can't modify any of this afterwards, right? We're not taking away any of the jobs from a level designer. This could, for example, be a really useful starting point where you first generate your level, and then a designer can go in and delete any of the parts they don't want, or completely rearrange a level, or perhaps even generate, use a smaller tool which just generates one single room and use that and place it around manually, right? That's also a workflow that someone could use. Next slide. So because it's Houdini and we're dealing with parameters which allow us to change properties of what it is we're generating, we can generate tons and tons and tons and tons of variations of a level automatically without having to do all too much work. So in this case, what we could do, a useful approach might be, is use something called PGG inside of Houdini, which allows us to create variations of a value we feed into a parameter and tell it, I want to have 1,000 variations of the parameter that controls the width of the level, or that controls the layout of the level. And then we can just render that to disk, giving us these images, and then we can cherry pick whatever level we want. So if we find one that we particularly like, we just pick that one, pick the parameter values that Houdini used to generate that, plug that into the system we have inside of Unreal, and we will get that exact level inside of Unreal. Let's go to the next slide. There we go. So to show you that I'm not lying or making all of this up, here is that exact HDA or Houdini digital asset inside of Unreal. And like you saw, I'm modifying the seed parameter for the layout, and already it completely regenerates the entire level. The materials, the geometry, the blueprints instantiates, the geometry, the effects emitters, the light placement, everything you see there. And to also show you how that looks like in Houdini, here is that exact output in Houdini. So once again, just that point cloud. To prove you that it is playable, and I did not make that up, we can just right click and say play from here. And then we can already play in that level that we have. So imagine how fast you can prototype your levels using Houdini Engine. It makes it really, really, really fast. So in this video, I'll be looking for some enemies, which takes a couple of seconds because I got stuck. That's what the obstacles are for, of course. And there we go. We have our enemies. And by clicking on our screen, we can just kill them. I think this is the top-down blueprint example that Unreal ships. So there we go. That was that. Next slide, and that's it. That's it for the first segment of the live stream talking about SideFXLabs. And yes, that is indeed me and Louise on screen. Shout out to Sasa Budimir for creating this graphic for us.
Almost worth playing a little bit longer.
Yeah.
Thank you, Paul. Let me go ahead and stop the screen share here. All right, there we're back. Quite a lot to cover. Let's see. Should we see if there were any questions related to your presentation before we move over to Mike?
Of course.
Let me just go ahead and bring that up. See, I couldn't leave focus on the presentation. That's when it stopped playing. That's what I noticed. Let's see. Will you be sharing the slide deck online?
Let's see. I don't think we have any sensitive information in there, so I could share those probably, yeah.
Okay, cool. We can go over that after the stream and get it up as soon as possible. Sorry, I didn't have the chance to look through the questions earlier. Did you have to follow some guidelines for width and height, or will it scale to fit the space given?
I'm assuming that's for the building generator. Yeah, so that's something I did not cover, but you might have seen it in the video. So that utility node that I created when I imported the module, that allows the user to specify what the width and height is of a module. So if you want it to always be a width of 4 units wide and 3 units tall, then that is the dimensions that the building generator will use to fit all the pieces. If you don't specify that value, it will just automatically measure that for you and make it fit. But no, there are no guidelines on how wide or tall you want your modules to be. The tool will adjust it for you. So if a piece is, for example, too tall that it doesn't fit in the floor, it will automatically scale it down so that it does fit, which of course will increase the repetition on the horizontal axis. But yes, that is possible. The tool does it for you.
You mentioned that there are some unique triangles per building. Are you using the undocumented pack node to separate these into different static meshes, or are they collectively one mesh?
Yeah, so there's a trick you can do with the engine where you can pack all the different pieces of geometry into a unique packed primitive in Houdini, and then use the Unreal split instance attribute, which you can find in the documentation, and that will automatically split it up into unique static meshes, meaning they will get culled if they're not on screen, instead of as opposed to having one giant mesh, which is not what you'd like.
How applicable are the workflows, etc., we learned with these tutorials to version 2 of the UE4 Houdini engine plugin?
So everything you can do in version 1, you will be able to do in version 2, plus a whole lot more. And what you can do more with that, I'd like to point you towards the forum post.
Had another a little bit more specific question here. They were wondering, how do we instantiate lights? I had no luck when trying it.
Right, so for lights, what I would recommend is create a blueprint out of it. So create a light, place it in your scene, create a blueprint out of it, or just create a empty blueprint, place the light in there, and then instantiate that. But you might also be able to instantiate just the component itself. But that's something you can find in the documentation.
Awesome. I think that were all the questions related to your presentation. Mike, are you ready to take over?
Yeah, let's see if we can figure out how to make this work. Screen. Okay. Make sure we have everything set up.
Looks all good over here.
Okay. Very quickly, probably should have said this before I started sharing screen, but I'm not going to switch back. So basically what I'm going to be showing today is kind of a high level overview of the new Houdini Niagara data interface, and a bunch of examples in both Houdini and Unreal. And because it's pretty high level, I have a feeling there's going to be a number of questions. So please feel free to ask the questions in the chat. I'll give some time after 1 or 2 examples to check in with Victor to see if there are any questions. And we'll also have some more information at the end of this, where you can find some resources to kind of help you out with that. So that's the one thing I want to mention. The other thing is, as you can see on screen, this is using 425. So in order to use the new data interface, because a whole bunch of cool stuff has happened on the Niagara side, we're pretty much 425 and forward. And you will be able to use Preview 7 to test some of the stuff out as of today. And the other thing is this is also Houdini 18 going forward, because some of the tools, some of the pieces to this workflow are in SideFXLabs, and that's where you'll find them. And lastly, a lot of what you're going to see today is program art. What Paul showed was really pretty. What I'm showing is not by any means as pretty, but hopefully the ideas will capture your attention, and we can kind of take it from there. Okay, so let's get into it. So at its most basic, the Houdini Niagara data interface is a way to get point cache data from Houdini into Niagara. Now, the previous version that we showed of this was basically what you just see in the bottom right, which was the static point cloud. And the idea was you could use it for triggering emitting particles for things like rigid body destruction simulations. But the #1 request we got was animated point caches. People wanted to do fluid sims and all sorts of other crazy stuff. And for the longest time, I said, no, that's a terrible idea. And eventually we gave in. So what you're seeing on screen is 4 ways or 4 types of data that you can bring across. The first one is a very simple particle simulation. And the ROP, the render node that will write out this data, will actually automatically calculate age and life attributes, which is what the data interface needs. But you can also explicitly set that. So if you do want to control that, you can add it. And then in the bottom left-hand corner, we have kind of this all-in-one example. You can literally take a point cloud, animate it either as particles or procedurally, add a bunch of attributes to that, and get all of that information across into Unreal. And then lastly, like I mentioned, is your static point cloud example, which is very similar to what you had before, and that still is pretty much the same. So this is kind of just a very quick look at what this is. Once I've exported that data from Houdini, I can bring it into Niagara as a Houdini point cloud cache, sample that data, and then feed it into things like position, as well as color and a bunch of other attributes. My microphone keeps changing on me. So this is kind of just a high-level overview, but I'm going to start breaking it down so we can kind of see what this looks like. Okay, so the first thing I want to talk about is how we're exporting this data, because in the past we were using a CSV file, which is like using XML. No one wants to do that. No one wants to use it. And so we're now using JSON as well as a binary JSON format to export that data. And you can use it for, like I said, static point clouds, procedural animations, particle simulations, rigid body sims, any kind of point cloud data, and you're good to go. This is a much easier process than what you had to do before with the CSV workflow. And hopefully it means that you don't have to think about this. You can just drop down the ROP, write out your data, and be right back into Unreal. So very boring code slide, but very quickly, I just want to give you an overview. This is the data that's being written out to the JSON file. We've gone for a format that has a header in it. So you actually have some information about how long the sequence is, what attributes are in there, what types of attributes are in there, and then it writes that all out. And we've designed it in such a way that you can write it out as ASCII. So if you want to debug it and see what's going on. And then when you're ready, you can also convert it to a binary JSON format. And the beauty of that is it will export really, really quickly, and it will import a lot faster than if it was ASCII. So you can now do much larger amounts of data and kind of get that feedback as you jump between the two packages. So let's talk a little bit about the modules. You'll see a little bit more of how they're being used as I go through some of these other slides. But basically what we've done is we've modified the modules so that they're very similar to how other Niagara sampling modules work. In other words, just like with sampling a texture or sampling a skeletal mesh, it will sample data and store that in a namespace. In this case, we have our own Houdini namespace. But in order to apply that to a position or a color of a particle, you would then set that variable on the particle emitter. So the modules will both sample through the update or also the spawn setup for the particle emitter. See if I'm missing anything over there. I think that's the basics of it. Something else that I wanted to mention, because if you have used the previous version of the Houdini Niagara data interface, the only way to sample data from the CSV file was by using the index, the column index of the attribute, which was a pain because if you started writing out in a different order, or if you had a lot of attributes, it was difficult to tell the difference between the two. So what we now have is you can actually use the name of the attributes, the attribute that you wrote out in Houdini. You can use that name in a node inside one of the modules in Niagara, which makes it a lot easier to find and call the data that you want from those point caches. So starting with our first example, this is the thing that everyone asks for over and over and over again, which is how do you get a particle fluid sim into Niagara? So this is how you go about doing it. So I'll talk through this a little bit.
See, I think we lost you there. Are you still with us, Mike?
I'm here. Can you hear me?
Yes.
Okay. Yeah, something decided to freak out on me. Okay, let me share that again. Portion of screen. There we go. We're back. We good?
We good.
Okay. So as I was saying, the particle fluid sim is what you're seeing in the top left-hand corner. This is actually using a tool that was created by one of our interns and is part of SideFXLabs. It's the Labs splatter tool. And once I've created that simulation, I can write that data out to a JSON file, and then bring it in and run it directly in Niagara. So this is actually controlling when the particles are spawned, the position of the particles. And if you have a look in the top left, you'll notice that the particles are lying on the ground, but on the right, they disappear. And they're actually not passing through the floor. There is a kill attribute on those particles, and that is being read by Niagara, and it's killing the Niagara particle in the simulation. So you can now finally get it in terms of actually meshing those particles. We don't have something for you there, but I believe Epic is working on something. I know that Ryan Brooks posted something on Twitter a couple of weeks ago. So hopefully we see some cool particle fluid meshing stuff happening in real time soon from the Epic side. I'll check now to see if there are any questions because I've just done a quick overview. If not, I'll start going to some more examples.
Let's see. Is the animated attribute cache deterministic? Will multiple renders look the same?
Is the cached? It is deterministic. So the simulation coming out of Houdini is deterministic. And the particle IDs, Niagara now does have a deterministic ID per particle that you can turn on as a flag. And so that's deterministic as well. So in terms of the data coming from Houdini, yes. In terms of how it connects to Niagara, yes. What happens in terms of Niagara simulation stuff, that's a separate part to this. But yeah.
I think that was it. There were a few more questions related to the level generator, but we can take them at the end of your presentation.
Okay, cool. So let's go back to this. Okay, so next example that I wanted to show is, remember that what we're doing here is we're just dealing with point clouds. And once we have attributes on those point clouds, we can do a number of different things. So as an example, what I did was I took a box and I used it multiple times to build this simple bridge prototype. On the top left, you can actually see each point that a box has been copied to. And then each point has a scale attribute that then changes the size of that box. And so what I get out of that is what you see on the right, which is kind of like this bridge prototype that I mentioned. So all I'm exporting to Niagara in this case is a static point cloud. It's just a single frame with position and scale and a type attribute that says whether or not it's the floorboard or the side pieces or the railed pieces along the top. So what I can then do is I can use those attributes in Niagara to basically use a mesh renderer on the particle emitter and change each particle mesh to have a different scale using that type attribute that I mentioned earlier. So that's kind of what's happening over here. And then from there, instead of running a simulation from Houdini, we're actually just using this as goal positions. So in this case, I've spawned a bunch of particles within a box location, and I'm using those original positions of those points you saw earlier as goal positions. So as the player gets closer, we're just using the user position here to then drive the simulation to move those pieces to their goal position. So I think this is pretty cool if you want to kind of do formation and destruction simulations where now we're kind of just using those points as underlying data to drive the Niagara simulation. Okay, so kind of carrying on this idea, this is something else that we came up with was, remember I said earlier that sometimes your simulations are not going to be able to run in real time. I mean, in Unreal, you can use Niagara, you can use Chaos, but even then, if it's a really complex simulation, you might start running into performance issues. And so the idea here is, well, what if you could take the Houdini simulation data and combine that with Niagara simulation data? So this is a relatively simple rigid body destruction simulation. The idea here is I've started with some goal positions. I move these spheres towards the center pillar, and then they all click into place in this structure. And so that simulation, that animation data, I can write out and bring into Niagara. But then I can do one more thing with it. So I can, first of all, I can instance a different mesh to those, but I can also have it interact. So what you're seeing here is initially it plays a Houdini animation. And then when the player gets close enough, I trigger something that then uses Niagara's physics to create an outward force, have them collide with the ground, use gravity, all that kind of stuff. So I think this is what I mean by kind of blending the two together, where you would do some stuff in Houdini and then the other stuff in Niagara to kind of create these more complex types of setups. Let's do one more, crowds. This was something I literally put together in the last couple of days. It wasn't going to be in the original talk, but thankfully it wasn't too bad to put together. I've always wanted to be able to do this because crowds can get quite expensive. It often requires an engineer to kind of implement it. And sometimes you just need kind of background crowds that are relatively cheap. So this is a crowd simulation running in Houdini. And what I've got is 3 different animations. I've got a standing animation, like just a standing in one position. I've got a walk animation, and then it actually converts into a zombie walk animation. So we've got these 3 different animations playing back. And then you can see there that I've taken the environment geometry from Unreal and brought it in and used that as a collider so that the crowd sim knows not to go past those bounds. And this is it running in Unreal. By the way, I really shouldn't have done stat FPS on this build because this is a dev build and the numbers do drop slightly. I checked it this morning and it sits at like 120 FPS the whole way through. So just a little note there. But essentially what I'm doing now is I'm running that crowd simulation through Niagara by using particle meshes and vertex animation textures. So now we get into some interesting kind of blending of different pieces of information. So the thing that's actually just coming into Unreal from Houdini is just these points, which are then, we're instancing the mesh. And the reason I go into wireframe is because the mesh, in fact, is just this T-pose that is then being changed by a vertex will position offset of a vertex animation texture. So hopefully this makes sense. And if it doesn't, feel free to ask questions and you can dig into the example files, which we'll be providing as well. So essentially I have here my mesh and I apply to that a vertex animation texture material. And what that means is I have written out the animation to the textures. That's what you can see in the bottom right-hand corner, the 3 different textures. And then I'm lerping between those textures. So as I change my clip blend value, it's driving the animation of the mesh. And so I can drive that value from my Niagara sim because I'm getting that data from the Houdini crowd simulation. So a couple of caveats that I want to point out here. I deliberately chose 3 animations because it was easy for me to lerp between 3 different values. You could add more to that, but it would start getting a little bit more complicated. But I think, like I say, for kind of relatively straightforward, I say relatively straightforward crowds setups that you want to bring into your game, I think this could be a good way to go about it that doesn't involve you having to build an entire AI logic system directly within the game engine. Okay, I'm going to stop there before I carry on and see if there's any questions about the stuff that I just showed.
For sure. We have a couple here. Let's see. Does the simulation go through Houdini Engine plugin or a different import situation?
Yeah, good question. So this is not using the Houdini Engine plugin. This is a little bit confusing, I'm sure, for someone who's not as familiar with Houdini and how it works with Unreal. This is, in fact, a Niagara data interface plugin. So this is a separate plugin from the Houdini Engine plugin, which you can install with Unreal. And so that's how the data is coming in. So it's being exported from Houdini as a JSON file. And then you would import that into Unreal the same way you would an FBX or a texture. And as long as you have the Houdini Niagara data interface plugin installed, it will pick up that JSON file, which we've named HJSON or HBJSON for binary, as a specific type of data, and then you can use that data in your Niagara simulation.
And there was one question regarding the low frame rate, and I think we had a bit of a combination of a GIF playing as well as Mike's upload speed just tanking right as we started your presentation.
Yeah, so like I said, I shouldn't have captured the numbers in there. I thought that would be a good idea, but I was using a developer build for that. And like I said, I was using 425 Preview 7 this morning with the plugin, and it was running perfectly at 120 FPS.
Yeah, we were definitely not even seeing 30 FPS on our end here, unfortunately.
Oh, really?
Yeah, it was tanking quite heavily due to the bitrate being a little bit higher. That's okay. Hopefully we can share the presentations later, and then you can get a good look at it.
Yeah.
Let's see. Someone is referring to the formation thing looks good. Do you make it in Houdini and you simply transfer it to Unreal? I'm not sure what the formation, maybe the formation of the crowds?
Maybe the rock formation. So yeah, that's done in Houdini. And the idea there is it's a rigid body destruction simulation that's directed. In other words, I'm starting from a position, I give it a goal position to go somewhere. When it gets there, then go somewhere else. And so we're mixing kind of art-directed rigid body simulation. So that's all being written out as a cache that's brought into Niagara and then played back just by moving the position of the particle.
What is the max points to cache from the flip sim?
Yeah, that's a good question, and I don't have a good answer for you. The reason for that is I think this is something that we really kind of need some feedback from the community about. We've done some tests, and it's run pretty well with thousands of points. And by the way, the data interface will work with both CPU and GPU particle emitters. So there's probably things you can do for performance reasons. But I think this comes back to kind of making games. You need to decide what you want to focus on in terms of where you want to let your performance be used up. And I think you could probably push this pretty high for a cinematic or something in the background, but it's really up to what your entire setup is rather than just looking at how many points you can get in. I mean, the number of points theoretically is as many as you want.
Is the JSON Houdini and Niagara exported live?
Yes, it is live. So at the end of this, I will be providing a link where you can go and download the plugin, the example file, and I should have a content plugin ready and available by the end of today.
And I'll make sure to add them to the announcement post as well under the little resources section there so that everyone can get it. Let's see, another performance question, I guess. How many crowd characters can be rendered on screen with ray tracing?
Oh, good question. So this is the interesting thing, actually. Oh, I wonder if it works with vertex animation textures. One of the beauties of, from what I understand with Niagara right now, is that you can do mesh instancing with ray tracing, and it's really, really fast. In fact, an example I'll be showing in a second deliberately plays into that example. So it's only a single draw call because there's only one material. I guess the big question is, because it's a vertex animation texture, if that breaks the performance attributes of ray tracing with Niagara particles. That might be a question for the Niagara team rather than myself.
I have Wyeth coming on in a couple of weeks, so
awesome.
Perhaps he'll be able to cover that. Are the vertex animation textures for the zombie folk shared per character, or is it unique across a giant mesh that has all the crowd geo?
So for this example, I've actually written out 3 separate textures. Each texture represents an animation. But you can, I think just given more time, I would have actually put that in a single texture because each animation is maybe 24 frames that loops. So that's 24 lines of a texture, 24 pixels in Y. So there's definitely a lot of optimizations here we could have done where we would have had one texture, one mesh, and played it all together.
I think the question, Mike, was not so much if you had a texture per animation. I think it was, did you have all the geometry that the crowds combined save as fat, or is it just one character and you instantiate it?
Yeah, thank you. Yeah, it's a single mesh. It's a single static mesh of a character in a T-pose. And that is being instanced to each particle in Niagara, just with a mesh renderer. And I've just had confirmation that vertex animation textures don't work with RTX in terms of performance. So
okay.
There we go.
See, so the crowd sim, and I think it's worth clarifying. So the crowd sim is a static sim meant for backgrounds without player interaction? Question mark.
I would say yes for the most part. It's something that I wanted to do. I just kind of ran out of time. If you think of the rock formation simulation, there's a combination there of the Houdini cache and then also interaction with the player. When the player gets close, we can exert a force on those particles. Something that I wanted to try with this crowd simulation is actually have the player run in between the crowds. Because if I just check the position from the particle to the player, then I can figure out a direction and kind of divert them. So you could kind of do like I say, a cheap version where you might not get a different animation playing on the crowd when the player gets close, but you could at least have the player moving through the crowd, and the crowds would kind of keep their distance. They would divert around the player.
How is motion blur computed with crowd using WPO? World position offset, I think is what
it's a good question. I believe, I mean, I know Niagara now does feed into the motion vectors for temporal AA. I'm not too sure. Yeah, I'd have to get back to you on that one.
Sounds good. That was all the questions for now.
Okay, cool. Let's keep going. I think I've got one more example, but there's a reason I wanted to keep this one. Okay, so this is kind of a combination of everything that I've shown so far bundled into one idea. So the idea here was we wanted to take an instance mesh, a static mesh, that we could put onto the Niagara particles specifically for the uses of ray tracing and RTX, which isn't in this demo, but hopefully something you'll see in the near future. And so what I wanted to do is have a wall of these objects that would almost create like a panel of mirrors. So what I've got here is a number of points with just an orient attribute that orients each one of these panels to those points. So that was kind of the initial setup that we have. The other thing that I've got here is a relatively complex rigid body simulation. So there's a number of things going on here. The balls that you see here are those same mirror panels that I showed in the previous example. I'm actually driving the position of those balls by an animated separate mesh. Those are the light gray, the dark gray templated geometries that you can see. And then we've got this really complex chain setup, which is all running through a rigid body simulation. And what I've also done is I've created a constraint between two pieces of these chains, so that what I can do is I can separate these out, drop them down, and that's going to be like my starting position. But then I can animate the constraints to pull them back together. So there's a lot of different stuff going on here. And you can see here it's playing back at 12 frames per second. That's not even simulation speed. That's just playback speed. So this is the kind of thing which would be really difficult, I think, to try and do at real time because of the number of interactions that are happening between those chain links and various other things that are going on. So the idea here is we want to go from that initial wall, burst things out using the Niagara simulation side of things, transition to something like this, and then still be able to interact with these because they are still particles in the world. And that's what this is. So there was that initial wall. Now we're seeing the particles are following the player. Then they actually move into their rest positions from that. And so now we're playing back that animation, but they're still interactive. So if I go in there, I can add a force to those particles in order to shoot them apart. And then I also added a trigger so I could have an event which spawned some sparks as well for that system. But this is kind of what I mean by there's we can now combine a lot of different things going on here. Ignore the stat FPS, by the way. But we're starting with a Houdini rest position. We're then transitioning into a Niagara simulation of moving the particles around, back into a Houdini cache simulation. And at the end there, we're actually adding forces from the Niagara simulation. So I think this is the kind of complex stuff that you can now do with the combination of these two packages because of the Houdini Niagara data interface. I'll let it play once more because it's cool.
It is cool.
So imagine RTX turned on with ray tracing and those mirrors actually showing the player. That's the idea. Hopefully it'll happen soon. Okay. Yeah. And so that is everything that I wanted to show for the data interface today. You can find more information here. I will give Victor the link as well. That link will take you to one of our forum posts where there is a link to a Windows version of the release 4.4.25 preview 7. There's also the example file, the Houdini HIP file that I used to show all the stuff that I showed today, as well as a link to the source code. So if you do want to build from source with your engine, then you can do that as well if you're doing Mac or Linux, or you just want to kind of keep up to date with Windows. And we'll be posting more information at that link over the next couple of days as we kind of flesh things out. And that's all I got today. Sure thing.
There you go. I was muted. Thanks a lot, Mike. We had 2 more questions come in. Someone was wondering, any way to get example scenes you have from Houdini and the JSON cache / Unreal project? Yeah,
so that's the link that I just showed on screen. And I don't know if you're putting it in chat, or we'll put it on the Epic forums as well. If you follow that link, you will get access to all of this stuff. You'll get access to the Houdini file, the data interface plugin, as well as the I'm finishing up a content plugin today, which will be available as well, which has pretty much most of the stuff in there.
Sweet, and perhaps we can head over to the forum announcement thread and update that there as well as it becomes available, so that every one of you who are watching this not live will be able to. It might possibly be live then already. That's great. Let's see. There were a few questions that came in. I believe that was more for Paul. Oh, this was a good question, actually. On the dungeon generator example, can it generate level streaming instances that are dynamically loaded / unloaded instead of just static meshes?
I think what you're asking is like for the pieces of geometry to be instantiated in a level that you can stream in and stream out. Currently with V1, no. With just a single HDA, I mean, you could have multiple, one in each level, and it generates that. That is one of the features that V2 will allow you to do. So it will allow you to directly write to a system that will composition, accept. So write to different levels.
All right. I think that was it. So another question in regards to the Vertex animated crowds. Could you use this to create a large crowd for a stadium?
I think so. Yeah, there's nothing stopping you from doing that. Houdini actually does come packaged with a bunch of crowd animations. So standing up, cheering, booing, all of that kind of thing. Pretty much what I showed today, you could write out those as Vertex animation textures. You could run the crowd sim to have it in a stadium, and then bring it into Niagara to run it there.
That sounds great. Lots of comments from chat saying you guys did a great presentation, so I just wanted to pass that forward since you might not be looking to that. Anything else you'd like to leave our viewers with before we end the stream?
If you're using SideFXLabs, we now have a Twitter at SideFXLabs. So if you're using Labs and you can show us what you're doing, show us. We'd love to see.
Yeah, it's a good point. We're always keen to see what the cool stuff that is being done by the community. We're often hard at work making these tools, and we don't always get the benefit of seeing the great work that everyone is doing with them.
That's great. Well, with that said, I'd like to thank both Paul and Mike for coming on the stream today and spending quite a bit of time preparing these presentations. Hopefully the quality came through all right for everyone that was watching at home. And before we end, I'd like to mention that next week there will be no Inside Unreal stream. However, tomorrow we're starting a new initiative that's called our educator live streams. Now, these live streams are specifically tailored for educators and students, but there's no reason why you wouldn't be able to tune in if you're just interested in what they are about. They're done by the education team, and you will be able to see them almost every Friday, I think, now for a couple weeks forward. I posted a schedule down in the Twitch channel description. Week after that, though, on April 30th, we will be covering highlights from 425 with James Golding. I'll have Marcus Vossmer and Simon Tourangeau on there. I think they're inviting some of the animators as well to go in depth in that a little bit. With that said, I'd like to thank everyone for watching today, and hopefully I'll have both of you back at some point, perhaps once the V2 has been released, and we can go over some of the new features of that. I think that would be great. That said, it's time to say goodbye. I hope you all have a great rest of your week, and we will see you all back on Inside Unreal again in 2 weeks. Bye, everyone.
Bye.